everyone, welcome back to Fuzzy Logic Lectures. In this video, we'll be starting a new concept called as classical and fuzzy logic. So what exactly is logic? Logic for humans is a way to quantitatively develop a reasoning process that can be replicated and manipulated with mathematical proofs. Or in other words, we can say that it is the ability of humans to reasonably think about something with the help of proper proofs and inferences. Now, the interest in logic is the study of truth in what we call as a logical proposition. So what is a proposition? Now, proposition is a collection of declarative statements that have either a truth value as true, which is represented by either T or a 1, or it will have a truth value as false that is represented by either an F or 0. Now, propositions are generally represented by variables. And an example of how a proposition can be is, suppose we have a statement, man is mortal. Now, this will return a truth value as true or 1 because man is indeed mortal. So, this is how proposition works. It's just a statement that has a truth value that is given by T or 1, or it has a false value that is given by F or 0. Now that we have understood what propositions are, let's move on to classical logic. So let's begin this lecture. In classical logic, a proposition P is a declarative statement contained within a universe of elements represented by X that can be identified as being a collection of elements in X which are strictly true or strictly false. Or in other words, we can say that a proposition, according to classical logic, is a set of elements where the truth value for all the elements are either all true or they're all false. So the truth value for an element P, which is given as T of P, will take the value as 1 if it is true, or it will take the value of 0 if it is false. That is, 1 is a condition when the element is all true and 0 is a condition when the elements are all false. Now we have an equation where U is the universe of all propositions, then T over here is the mapping of the elements U in this proposition, which is the set to the binary values 0 and 1. Or we can say that if all the elements U in the universe capital U that are true for the proposition set P are called as a truth set of P denoted by T of P. And all the elements U in the universe U that are false for the proposition set P are called as the falsity set of P. That is, the truth set of P denoted by T of P will take a value of 1 and the falsity set of P will be taking a value of 0. So this is how proposition is working in case of classical logic. Now for a universe X and a null set phi, we will define the truth value as T of X is equal to 1, as I've mentioned here that if it is the truth set of P, we will take the value as 1, and T of phi is equal to 0, as I've shown over here that the falsity set of P will be represented by 0. Let's move on to the next topic, which is connectives. We have another term called as connectives. Now these connectives are what connects the propositional statements together to form new propositions. So if you have two propositions P and Q on the same universe, they can be combined to form a new proposition. And this combination can be done using 5 logical connectives. And they are, first we have disjunction, then we have conjunction, then we have negation, then we have implication, and finally we have equivalence. Let's take a look at each of the connective one by one, starting with disjunction. Now the disjunction connective or logical OR is a term used to represent inclusive OR. Now the disjunction is very similar to union operation. Now the difference between OR and logical OR is that OR represents exclusive OR. That is, it represents exclusive OR, whereas logical OR represents inclusive OR. So what is the difference between exclusive OR and inclusive OR? The main difference is that if we have inclusive OR, it allows both possibilities as well as either of them. For example, if we have two variables A and B, then in the case of inclusive OR, if either A is true or B is true, or if both A and B is true, then the final statement value will be equal to true, or the final statement will be true. But in the case of exclusive OR, if either A or B is true, then and only then is the statement value true. So this is the basic difference between exclusive and inclusive OR. Here in the case of disjunction, we mean to say it is inclusive OR. That is, a compound proposition will be true if either of the simple propositions are true or both are true. So let's take a look at the truth table for disjunction. Here we have two propositions P and Q, and we have the propositions which are joined by the disjunction connective over here. First, we'll put the values of P as true, true, false and false, and for Q we'll put it as true, false, true and false. So what we're doing is we are testing out various combinations and checking what is the value of the final statement. So initially we can see that P value is true and Q value is true. And according to the disjunction connective, we have learned that if either P or Q is true, or if both P and Q is true, then the final statement will be true. Hence, since both P and Q is true, we can put the final statement P disjunction Q as true. In this case, since P is true, although Q is false, and in the case of disjunction, only either one has to be true or both can be true, we can take this as true. Similarly, in this case, we can take this as true since the Q proposition is true. Lastly, we can see that the P proposition is false, Q proposition is false, therefore P disjunction Q will also be false. So this is how you do the disjunction connective, and this is the truth table for the same. Next, we'll move on to conjunction. In the case of the conjunction connective, if both the proposition P and Q are true, then the compound proposition will also be true. So technically we can say that this performs the AND operation or the intersection operation. Let's take a look at the truth table. So initially we'll put this as true, true, false and false, and here we have true, false, true and false. Now according to this, if both the propositions P and Q are true, then only the compound proposition will be true. So only in the first case, since both P and Q are true, we will get the final statement as true. In all other cases, it will be false. So this is how you do the conjunction connective. The next connective that we have is negation. So according to the negation connective, the negation of a proposition P is false when P is true and vice versa. So if you take a look at the truth table, we get if the proposition P is true, then the negation of the proposition will be false. Similarly, if the proposition P is false, then the negation of the proposition will be true. So this is how you do the negation connective. Moving on to the implication connective. In the case of the implication connective, it is represented as P implies Q, which means that if the P proposition is true, then the Q proposition must also be true. It is also understood and written as if P then Q, where P is called as the premise or the hypothesis and Q is called as the conclusion. Let's take a look at the truth table for implication. As you can see, here we have the P proposition, Q proposition, and it is connected by the implication connective. So initially let's fill the truth table as in P as true, true, false and false, and Q as true, false, true and false. Now to understand this truth table properly, let's consider an example. Suppose you have a statement as, if you score 90% or above in this subject, then you will get an A grade. So here, the P proposition is you scoring 90% or above in this subject, and the Q proposition is you will get an A. Now what this statement means is that you are going to be guaranteed with an A grade provided that you score 90% or above in this subject. Now let's consider the first condition. Over here, suppose you score 95% in the class, and if your final grade is A, then the promise was kept and hence we can consider the overall statement as true. Because you scored 95% or above in this subject, which means the P proposition is true. And you have got an A grade, which means that your Q proposition is also true. So therefore, the promise was kept, and hence we can consider the overall statement as true. Therefore, here P implies Q will be true. In the next case, however, your grade is not an A even though you scored above 90%. That means you have scored a 90%, as in your P proposition is true, but your grade is not an A, that is your Q proposition is false. Then the promise was broken and hence the overall statement is false. So over here, if P is true and Q is false, then P implies Q will be false. Now consider the situation in which you do not score 90% or above in the subject. So what will happen, and will the final statement be true or false? Now it is a very important thing to note that this particular statement does not say what grade you would receive if you scored less than 90%. So for example, if you score 82% in the subject and receive a B grade, you cannot say that the promise was broken. And if you score 82% and end up with an A grade, you still cannot say that the promise is broken. So when the premise or the hypothesis P of the implication P implies Q is false, then in that case it is a very tricky situation. We cannot say that the implication is false, yet we have no evidence to say it is true since P did not happen at all. Therefore, we will consider this situation as vacuously true. That is, we use the term as vacuously true. Now, what does vacuously true mean? The term vacuous truth is a conditional or universal statement that is true but not in a meaningful way. For example, suppose you are in a room full of people and none of them have a phone with them at all, and you get up and declare that all phones in this room are switched off. Now this is technically true because no one has phones in their hand, so any phone in the room can be considered as switched off. That is why in the last two cases of the truth table, P implies Q will be taken as true, or it is taken as vacuously true. The point here is that the use of implies in logic is very different from its use in everyday language to reflect causality. Another way to look at this is through a statement, innocent until proven guilty. So this is taken as an if-then statement which is considered to be true until it is proven false. Since we cannot call the statement P implies Q as false when P is false, our only alternative is to call it true, and hence we get the truth table value as follows. So it is very important to note and to remember that a false statement can imply anything. Let's consider another example for implication. Consider the following implications. If hydrochloric acid and sodium hydroxide are combined, then table salt or NaCl will be produced. The second statement is, if January has 31 days, then dogs are mammals. Technically, both these statements are true. That is, the first statement is an example of the cause and the effect, and is going to be reflected by the chemical equation HCl plus NaOH, which will give us NaCl plus H2O. That is, both these propositions are true, hence the implication will also be true as per our truth table. In the second statement, we can see that there is no causal relation between the days of the month and the dogs being mammals. Both the hypothesis and the conclusion of statement 2 are indeed true. So, according to our truth table, this implication will also be true. So basically the point that I am trying to convey here is that the use of implies in logic is very different from its use in everyday language to reflect causality. So this is how implications work. Let's move on to the next connective, which is equivalence. In the case of equivalence connective, it generally arises when we have dual implications for propositions P and Q. That is, if P implies Q and Q implies P, then we can say that P is equivalent to Q. That is, if both P and Q are false or both are true, then the compound proposition will be true. So as per the truth table, again we'll put true, true, false, false, true, false, true and false. And as I've said earlier, if both P and Q are true or if both P and Q are false, then only the equivalence connective will be true. That is, true and true will give us true, false, false will give us true, the rest they'll all be false. Because P has to imply Q and Q has to imply P, then only we can say that P is equivalent to Q. This is all about the equivalence connective. Now consider we have sets A and B from a universe X which contains it, and P and Q are two propositions given as P proposition measures the truth of the statement that an element D from a universe X is contained or present in set A, and the proposition Q measures the truth of the statement that an element D from a universe X is contained or present in set B. So we can say that if D belongs to A, then the truth of the proposition is taken as 1, otherwise the truth of the proposition is taken as 0. Similarly, if D belongs to set B, then the truth of proposition Q is taken as 1, otherwise the truth of proposition Q is taken as 0. Because as we have seen earlier, 1 represents the truth value and 0 represents the false value. So when we look at the connectives, first we have disjunction. That is P disjunction Q, where the element D belongs to set A or the element D belongs to set B. Hence we can say that the truth of P disjunction Q is given as maximum of T of P and T of Q. In the case of conjunction, we have P conjunction Q where D belongs to set A and D belongs to set B. Hence we can say that the truth of P conjunction Q is given as minimum of T of P and T of Q. Then we have negation. That is, if T of P is equal to 1, then T of P negation will be equal to 0. Similarly, if T of P is equal to 0, then T of P negation will be equal to 1. Then moving on to implication, we can say that P implies Q where D does not belong to set A or D belongs to set B. Hence we can say that T of P implies Q is given as T, P negation union Q. Next we have equivalence, that is P is equivalent to Q, where T of P equivalent to Q is given as 1 if T of P is equal to T of Q, and will be equal to 0 if T of P does not belong to T of Q. So this is how the whole connectives and the operations take place. I hope the concept of propositions and connectives is clear by now. Moving on to the next topic, which is tautologies. In the case of classical logic compound proposition, when the truth value of the compound proposition is always true, irrespective of the truth values of the individual simple propositions, then it is called as a tautology. For example, if you have two simple propositions P and Q, irrespective of whether P and Q is true or false, the final truth value of the compound proposition will always be true in the case of a tautology. So if a compound proposition can be expressed in the form of a tautology, then the truth value of that proposition will always be true. Now let's see two types of tautologies. We have Modus Ponnes and Modus Tollens. Let's start with Modus Ponnes. In Modus Ponnes, the tautology is given as P conjunction P implies Q, where the entire thing implies Q. This means that if you have two propositions P and P implies Q, and if they both are true, then the truth of the proposition Q will automatically be inferred or implied. So this is what the Modus Ponnes is. Let's take a look at the proof of Modus Ponnes. Now I have added these properties for your reference since we will be using this to prove this tautology. Now if any of you have any doubt in how these properties have come, please refer lecture 1 of our fuzzy logic playlist. I have included the link in the description given below. So let's begin with the proof. We have P conjunction, P implies Q, the whole thing implies Q. Now this P implies Q can be written as P bar union Q. That is, P conjunction P bar union Q, the whole thing implies Q. Now this can be further distributed with the help of the distributivity property. That is, we can write it as P conjunction P bar union P conjunction Q, the whole thing implies to Q. Now when we look at the excluded middle, we can see that A intersection A bar is equal to phi. So here we have P conjunction P bar. As I said earlier, conjunction is similar to that of intersection. Hence, P intersection P bar is taken as phi. So we have phi union P intersection Q, the whole thing implies to Q. As per the identity property, we can say that A union phi is equal to A. Therefore, P conjunction Q union phi will be equal to P conjunction Q. So we have P conjunction Q, which implies Q. Once again, we'll apply implication. That is, we'll apply implication over here. We will have P conjunction Q, the whole bar union Q. Now applying the De Morgan's property to this, here we can see De Morgan's law, which is given as A intersection B whole bar is given as A bar union B bar. So we can write this as P bar union Q bar union Q. And now let's apply the associativity property to this. So we'll have P bar union Q bar union Q. And as per the law of excluded middle, we can say that A union A bar is equal to the universe X. Therefore, Q union Q bar will be equal to your universe X, or P bar union Q bar is equal to X. And as per the identity property, we can say that A union X is equal to the universe X. Therefore, P bar union X will be equal to X, which is a universe X, and we know that T of X is equal to 1. Therefore, we have proved that our tautology is true. To understand this proof better, let's consider the truth table so that we can prove for Modus Ponnes. Here we have P, Q, P implies Q, P conjunction P implies Q, and P conjunction P implies Q, the whole thing implies Q. So let's write this as true, true, false, false, true, false, true, and false. Now from what we understood from the truth table of implication, we had if P is true and Q is true, then P implies Q will be true. If P is true, Q is false, P implies Q will be false. And when P is false, Q is true, it will be true. And when P is false, Q is false, it will be true. Next we have P conjunction P implies Q. That is, we have to consider this column conjunction this column. So as per the truth table for conjunction, if we have P is true and P implies Q as true, then it will be true. And if we have true and false, it will be false. If we have false, true, it will be false. And false, true, it will be false. Lastly, we have P conjunction P implies Q. The whole thing implies Q. So we have to consider this column implies this column. So we have true and true, which is it will be true. Then we have false and false, which implies it will be true. We have false and true, which implies it will be true. And lastly, we have false and false, which implies it will be true. Therefore, we can see that the tautology is taking all true values and therefore it has been proved. Next, we'll move on to the next tautology, which is Modus Tollens. The Modus Tollens tautology is given as Q bar conjunction P implies Q, the whole thing implies P bar. So let's take a look at the proof of this tautology. And as usual, I have put forward the properties for your reference. So let's start with the proof. We have Q bar conjunction P implies Q, the whole thing implies P bar. So first we'll apply the implication. So we'll have Q bar conjunction P bar union Q, the whole thing implies P. Then we'll apply distributivity property. So we'll have Q bar conjunction P bar union Q bar conjunction Q, the whole thing implies to P bar. And next we apply the excluded middle, which is A intersection A bar equal to phi. Here we have Q bar intersection Q, which will be equal to phi. So we have Q bar conjunction P bar union phi implies to P bar. Now as per the identity property, we know that A union phi is equal to A. Therefore Q bar conjunction P bar union phi will be equal to Q bar conjunction P bar as per identity property, and this implies P bar. Now once again apply implication. We have Q bar conjunction P bar, the whole bar union P bar. And applying the De Morgan's law to this, we get Q union P bar. And when we apply associativity to this, we get Q union P bar. And as per the excluded middle, we know that A union A phi is equal to the universe X. That is, P union P phi will be equal to universe X. Therefore, we get Q union X. And we know that by applying the identity property where A union X is equal to X, we will get Q union X will be equal to the universe X, and we know that T of X is equal to 1, and hence the tautology is proved. Now let's also prove it with the help of a truth table. We have true, true, false, false, true, false, true, false. Now negation of P of true will be false. Here it will be false. Here it will be true, and here it will be true. Similarly for Q bar, that is negation of Q, T will become F, F will become T, true will become false, false will become true. Now for P implies Q, we have true and true, which will give us true, true and false, false, false and true is true, and false and false is true. Then next we have Q bar conjunction P implies Q. That is, we have to consider this column conjunction this column. So we have false and true, which will give us false, true and false, which will give us false, false and true, which will give us false, true and true, which will give us true. Then lastly we have Q bar conjunction P implies Q, the whole thing implies P bar. That is, now we have to consider this column implies this column. So we have false and false, that is, false and false will imply true, false and false will imply true, false and true will imply true, and true will imply true. Therefore, we can see that the tautology has all true values. Therefore, we can say that the tautology is proved. So this is how tautology works, as in we have to get a true value for the compound proposition at the end. Now let's take another example to prove a tautology. The question given here is that to show that P implies Q, disjunction Q implies P is a tautology. That is, when you consider the truth table, over here all the values here have to be equal to true, or they have to be equal to 1 to show that this is a tautology. That is, the final compound proposition should always be true for it to be considered as a tautology. So let's fill the values. We have true, true, false, false, true, false, true and false. P implies Q. Here P and Q both are true. So P implies Q will be true. Here P is true, Q is false, so it will be false. P is false, Q is true, therefore it will be true. And when both are false, it will be true. Then in the case of Q implies P, Since both are true, Q implies P will be true. Here Q is false, P is true, therefore it will be true. Then here Q is true, P is false, so it will be false. And finally Q is false, P is false. Since both are false, it will be true. Lastly, we have P implies Q, disjunction Q implies P. So when both are true, we will have true. When one of them is true, we will have true. One of them is true, it is true. And when both are true, it will be true. Therefore, we have proved that P implies Q, disjunction Q implies P is a tautology. So this is how you prove a given statement or a given expression as a tautology. You can also prove this tautology with the help of the algebraic method that I have shown earlier, but a truth table is much more easier to understand and easier to prove. Moving on to the next question. Show that P implies Q, conjunction Q implies P is a tautology. Now this question is a homework to all of you. If anyone has any doubts in any of the concepts taught in this video, please feel free to ask in the comment section below. Either me or another viewer will surely help you out. If you found this video to be helpful, please like the video and support us by subscribing to the channel. In the next lecture, we will be continuing with the remaining concepts in classical logic. Thank you for watching Topperly and have a great day.